Today, I want to give you another hand rule. This is going to allow us to find the magnetic field and therefore the polarity of a solenoid. Or a solenoid is a coil of wire with an electric current going through it. We're called the Coil rule because a solenoid is. Now, this Coil rule for solenoids is going to allow us to find a magnetic caused by this coil of wire, but it's also going to allow us to find the polarity of this coil of wire. This is effectively an electromagnet. You get an electron current going through the wire. It generates a magnetic field. If there's something inside of this steel core or iron core, and this iron core becomes a magnet. It becomes like a probe. You guys have made them in school. All of you guys have seen those in TV and movies, like a junkyard. And all of a sudden, this crane is able to pick up this big car just by sticking something to it. And then they flip off the switch, the car falls down. They've just made an electromagnet by turning on the electric current through that coil of wire, through that solenoid. So how do we find the polarity of this? How do we find the direction of the magnetic field? We're going to use this coil rule, which is, by chance, exactly opposite to the rule that we learned on Friday. It's exactly opposite to the wire grasp rule. The wire grasp rule said you stick your thumb in the direction of the current or in the direction of the moving charge, and you stick your fingers, your bent fingers, in the direction of the magnetic field. In the coil rule for solenoids, it says your thumb will point in the direction of the magnetic field and your fingers will point in the direction of the current. Here's what I'd like you to do right now, everybody. I'd like everybody to take a piece of scrap paper, which I'm handing out right now. Make a little solenoid. It's arts and crafts class today in Physics 30, boys and girls. I want you to roll it up. If you have trouble doing that, follow the instructions given by your teacher. Roll the paper up, just like this. Once you have it written up or rolled up, I want you to take a pen or a marker or something that makes visible lines, and I want you to write a word on the front of it. The word I want you to write on the front of it is front. What else would you write on the front of it? You should have a coil with one word on it that says front. Now that everyone has a pretty little arts and craft project made for the day, your solenoid, what I want you to do is this. Hold your solenoid up in front of you so that you're looking at the word front. Label it. Roll it up and write the word front on it. Everybody's looking at the word front now. If you look at this picture up here, you can see that they've got the electric current labeled as going up in the front. You can see the wire kind of goes around like this. And the electric current's going to go up in the front as labeled on that diagram. It's therefore going to go down in the back. Up in the front, down in the back. Up in the front, down in the back. That's given to us. Now what I want you to do is, using the coil rule for solenoids, stick your fingertips on the word front. Literally, with your fingertips front. Touch the word front with your fingertips, with your left fingertips. Not your right ones, your left ones. Okay? But they have to be pointing up. You have to touch the word touch the word front, and they have to be pointing upwards. Because look, your fingers point in the direction of the current, and the current is going up in the front. So my fingertips have to touch the word front up in the front. Now what I want you to do is, okay?
I don't know.
Once you have your fingers touching the word front, pointing up in the front, just like this, And I want you to bend your hand a little bit. But you got to keep your fingers on the word front. And they got to remain pointing up. If you do this, your thumb should be automatically pointing to the right. That means the magnetic field is inside the coil is pointing to the right. Meaning this end is what? South or north? No. The magnetic field goes from south to north inside. It goes from north to south outside. You could continue drawing the magnetic field around this way outside from north to south. It's not necessary, but it's fine to do that. Okay, if it makes it easier to see it that way. Okay, bottom line is my thumb points in the direction of the magnetic field inside the coil, which is toward the north. Let's try another one here, okay? Since you guys did so well on that one, we'll do another one to make sure that it wasn't just a fluke. Here's my piece of steel. There, by the way, doesn't have to be a piece of steel or some kind of ferromagnetic material inside, but it serves two purposes for us if we do put one inside. Number one, it increases the strength of the electromagnet, because what this piece of steel or ferromagnetic material does is essentially stores the magnetic field, right? So it makes it a stronger electromagnet. And it also makes it easier to draw. Okay, it's easier for me to draw it if I put something inside it, like a piece of steel or a piece of iron. Here's my wire. See the way this wire is set up, guys? Okay, you see the loop of wire in front, and then it goes behind. You can't see that because there's something in the way, right? But it's there. There's my battery, my power supply. Every power supply has a negative terminal and a positive terminal. The negative terminal is always the short end, the small end, and the positive terminal is always the long end. How do I remember that? I remember that, well, because I've done it so many times, but even if I hadn't done it so many times, my way to remember that is to say, look, the positive end, the only end that has the only terminal that has a vertical line in it, right? Negative doesn't have a vertical line, positive does. The one that has a vertical line in it has the longest vertical line in the power supply. The one that has the shortest vertical line has no vertical line in the symbol. So positive end is the left side, negative end is the right side. That means electrons will leave the negative end. They'll go up in the back, and then they'll come back down in the front of this wire. And then they'll go back around to the power supply. So we got a current that's flowing counterclockwise here. Let's figure out what the polarity of this coil is now. Which end is north, which end is south? Okay, there's my coil. You're looking at the word front. I want you to stick your fingers on the word front. Which way should they be pointing on the word front? Yeah, should be pointing down. Now start with them there. If when you clench your fist, they kind of curl around a little bit, that's okay, as long as you don't take your hand off. Yeah, that's good. And then you just stretch your thumb out, 90 degrees to your hand. You know, like you're hitchhiking. Okay, 90 degrees to your hand. Which way is my thumb pointing? To the left. So the magnetic field inside this coil is to the left, meaning that this end is what? North or south? Right? It's north. The magnetic field inside is north. It goes from south to north. So that end's north, that end is south. Yep. Yep. Hey, the good news here, if we have a battery set up one way, it's got to be north-south. If we have it set up the other way, it's got to be south-north, right? Let's try this. Let's try another one. Look at that. That's set up the same way, right? The battery has negative terminal on the right side, positive on the left side. The electric current goes this way. Counterclockwise once again. Look at the word front on your little craft that you made a few minutes ago. Stick your fingers which way on the word front? Up on the word front. Curl your hand around and maybe your fingers move a little bit. That's okay. Just make sure your thumb is 90 degrees to your fingers. Which way is my thumb point? Towards the right. Wait a second. How is it possible for a counterclockwise current to produce two opposite magnetic fields there? What's different about these two problems? Yeah, Nathan? Yeah, the way the coil is set up. Listen, don't try to memorize these. Okay, don't try to memorize these. You're going to start getting mixed up if you memorize it. Okay, invest the time to learn how to do it. It's quiz day, it's test day, whatever. Roll up a piece of paper, write the word front on it. That's not cheating. Okay, grab a piece of scrap paper, write the word front on it, and do this. If you have to, then do this. Figure out that the magnetic field points opposite because the coil was wrapped opposite. Let's try one more here. Oh, this one's going to be a tough one. Without looking at anything you've already done, I want you to draw the magnet in here. Sorry, draw the battery in here. So we've got the direction of the polarity that's induced by this current. This is not a magnet inside here, a permanent magnet inside here. It's just a magnetic field that was produced by the electric current in this solenoid. Got a south on the left side and north on the right side. Okay, what direction does the current need to be, and therefore what direction does the battery need to point in order to get the polarity that we have shown here? So how do we do this? How do we do this? Well, look, let's grab our little craft that we made a little while ago in arts and crafts physics class. Let's look at the word front. Let's stick our fingers. Oh, wait, we don't know which way to stick our fingers because we don't know which way the current is. What do? We stick our thumb in the direction of the magnetic field, which is from south to north, inside the coil. So let's stick our thumb towards the right-hand side. Stick your thumb towards the right-hand side. And then I want you to grasp it. Okay, I don't care where you grasp it. In the end, move your fingers around so that they're pointing, oh, look, up in the front. If my fingers are pointing up in the front, then that means my current is going to go up in the front, down in the back, and around like this. Which end is short, which end is long? This one's going to be long or short? So it's going to be short. That's the negative end, and that's the positive end. Is that okay? You don't have to copy down what I'm about to show you right now. It's just a couple examples, okay? What do you see on the board right now? What is that? Nathan, what is it? That's a speaker, right? A speaker is a pretty simple device, actually. This isn't something that you have to know. But we want to go through examples just like we did with, remember, the electrostatic fence painting and so on, just so that you become familiar with working things out. There's a good chance on a diploma exam you might see some application of one of the hand rules or of magnetism or electromagnetism, whatever. And you know what? It could even be this exact thing. It's not likely to be, but it could be. Okay, it's just as much chance of having a speaker on there as anything else. But when you look at the almost infinite number of possibilities, probably not going to see this again. That's okay. Okay, it's still useful to work through this. This speaker consists of three main things. There's the cone. This part right here, the cone, which is made out of, usually it's like a felt material, sometimes a cardboard material. Some cones are better than others depending upon what the material is. That cone is attached to a permanent magnet right here, this entire yellow thing, the permanent magnet. And kind of threaded around and in between that permanent magnet is a coil of wire, a solenoid. That solenoid, that coil of wire, is attached to wires that go to whatever is generating the sound. It's your iPhone, it's your computer, it's your stereo, it's your television, whatever. Those wires go to your iPhone or whatever. And those wires carry an electrical signal from your iPhone or from your television or whatever the case may be. And that electrical signal is generated by the sound. You've got an electrical signal that's proportional to the sound that you want to produce. That electrical signal goes through the solenoid, the coil of wire here, and that generates a magnetic field. But it's a changing magnetic field because the sound is changing. As the magnetic field changes, as the sound changes, it changes the electric current, which in turn changes the magnetic field. As that magnetic field changes, it causes a different effect on the permanent magnet. So at one moment, it may be pushing the permanent magnet this way. Another moment, it may be pulling the permanent magnet back this way, depending upon the electrical signal that's going through this solenoid. Now, if it's pushing it out, that actually as it pushes it out and as it pushes the cone out with it, it creates a high pressure area out here, right? You give that cone a really quick push outwards, you've got a really high pressure area there because all this air has been compressed. But if you pull it back, you create a low pressure area because the air's been sucked back. High pressure areas and low pressure areas in air are otherwise known as sound. You've just generated sound. Remember in Physics 20, sound is a series of compressions and rarefactions, a longitudinal wave? That's exactly what we're making there, is a longitudinal wave. So by sending this electrical signal to this solenoid, which causes this magnet to go in and out by force of attraction and repulsion, and causes this cone to go with it, you're generating sound. Again, one more application for you here. What's this? What's this? Yeah. Yeah, it does look a lot like a fire bell, actually. This could be a fire bell for sure. There's a switch on the fire bell up here. Now, this switch, difference between this diagram and a fire alarm would be that when you flip the switch on a fire alarm, it stays on. Okay, so you don't want to just push it and have to hold on to it. Otherwise, nobody's going to push the fire alarm because you're going to be the last person out. You push the switch, you flip the switch on the fire alarm, and it stays on, right, until there's a master switch that turns off. Oh, look at the way it's set up right now. Right now, before I flip that switch on, okay, you can see that the switch is beside a power supply. That power supply has a negative end and a positive end. And you can see that they follow it around here. No current right now going through it, right, because the switch is off. But you can see if you follow around it, there's this make-break contact right here that's touching this piece of steel that's in contact with this, touching the hammer, goes around like this through the loop, the coils, and so on. Right? So we got a complete path except for right here. Nothing happens right now. It's turned off. What happens, though, when I push that button and that switch is turned on? Well, then all of a sudden electrons start flowing this way, counterclockwise. They go through the make-break contact. They go into this little piece of steel right here. They go through here, through the electromagnets, back around here, and they keep going around. Good? You got a complete circuit. Whoopee. Big deal. What do these electromagnets do? What's the purpose of those guys? Yeah, go ahead. Yeah, go ahead, Bryce. Wouldn't they what? Yeah. So this metal bar right here gets attracted to it. As it gets attracted to it, this hammer comes with it. What happens to the hammer as it gets pulled to the right? Hits the bell, right? What do you hear? Ding. Not ding, 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 ding that you need for a fire alarm. You hear ding. What else happens in that process? Well, as that blue rod gets pulled to the right, this make-break contact is broken. So even though the switch is still on, the current stops flowing because there's no complete path now. It's not turned off at the switch, it's turned off at the make-break contact. Good? Now there's no current flowing. So what happens to this hammer in this blue rod now? Doesn't stay there, because if you can see, I don't know, it's pretty hard to see this on the board, I guess. There's a spring right here that's now stretched. That spring pulls it back. So it pulls it back, the hammer away from the bell, and it pulls back this blue rod here away from the electromagnet. Makes contact again. What happens when it makes contact? Current starts flowing. These become electromagnets again. What happens? Hammer gets pulled toward the bell, ding, breaks contact. Electromagnets aren't electromagnets anymore. They're just coils of wire. Okay, goes back, completes the circuit. Electrons start flowing through the electromagnets again. They become magnetized again. They pull the hammer and this blue rod toward it. Ding. The cycle repeats itself hundreds of times. Ding, 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 ding. That's your fire alarm until someone flips the switch off. Make sense? It's easy, right? It's simple, right? Really, when we introduced the concept of Ørsted and electricity from magnetism on Friday, we said that just about every bit of technology is based on this, at least in part. From your iPhone, to your computer, to your doorbell, to your fire, for heaven's sake, to your speakers that you listen to your music from. Everything has Ørsted's discovery embedded in it. Okay, got a little bit of homework.